thanks everyone for coming. This is the first talk in our new seminar series, optimization in ML and AI. So I'm very excited that Courtney's here to kick it off. We have about 8 speakers for the full event planned out, about 1 month. So there'll be more emails coming later on. So, but like I said, I'm very excited to have Courtney kick it off for us. Courtney is probably, if you know her, she's very distinguished now. She's an associate professor at McGill University. She has won lots of awards, but maybe the most impressive recent ones were the Sloan Fellowship and the CFAR AI Chair. And so she'll tell us about high-dimensional optimization of machine learning with applications to compute optimal neural scaling.
Is that a speaker? Is that a speaker?
Speaker? You can take it loud.
Oh, louder? Oh, maybe I can move this. I think it's here. There's a mic. Can you hear me better? Okay. I'll try not to move, but I tend to move around, so I apologize. We're working.
This is the goal. So we
Go higher. Okay, perfect.
Thanks.
All right, good. All right. So thank you, everyone. Dima was my PhD advisor, so he probably still thinks of me as a student. So this is, I'm going to talk to you today about some work that I did with Google DeepMind. It started there and then it sort of expanded. So, and I just want to highlight a couple of people, especially Damian, who's a PhD student. He actually did this in his first year, his PhD, and quite impressed. And today I'm going to talk to you really about scaling laws. Please ask questions as we go through. A lot of people here probably maybe have never heard of a scaling law, especially this compute optimal one. So please ask. Okay, and I'll try to be gentle going through all of this. Okay, so what are the challenges we see in machine learning and optimization? The main challenge we see, right, is that our problems tend to be what I'm going to call high dimensional. So we have not just a large number of samples, but we also have a large number of features deep. And then we tend to run stochastic algorithms to solve these types of problems. So, but because these things are stochastic, before we actually start running any algorithm, we have to choose a bunch of things. So we have to choose stuff like the hyperparameters for the algorithm. That's the one you're probably most familiar with. But you also, in neural networks, which is very different than in things in the past, which is you also get to choose the number of parameters. You get to pick the number of neurons that you use. That's something. You also get to choose your architecture. So these are things, other choices that you may not have known beyond the hyperparameters. So what did we do before these models got extremely large? So before they got large, we just basically trialed and errored our way through it. We just tried some D for our size that we're going to minimize over, and we saw that it worked. If it didn't work, we just retried it again. But the models have gotten so big that we cannot do this anymore. So we cannot just trial or error our way through things. We only actually get one shot at running that stochastic algorithm. That's it. So we have to choose beforehand everything. So in particular, how do they actually do it? The way they actually do it in practice now is that they have to know how the algorithm and the architecture all scale. So how the optimization problem scales is you change the number of parameters, you change the number of samples, you change the algorithm and the hyperparameters. And this is going to be related to something called compute efficiency. So the idea here is then that we need a really good optimization theory that actually predicts behavior in practice. Because now theory is mattering here. We have to know how these things scale. They can't trial and error their way through. So what do I mean by good optimization theory? I mean something along these lines, which I'll talk about, which is that what I mean is to be able to actually predict at any iteration of my stochastic algorithm exactly what the loss will do. So here I am running an SGD on real data here. So this is CFAR 5M, and SGD is a squiggly line, and I need to be able at any iteration of my algorithm actually predict what that loss is. And that's what these lines are here. And I need to be able to do this as I vary the number of samples and the dimension. Okay. I will come back to this, but pay attention. This is the spectrum of the covariance of the data of CFAR 5M. Notice that log eigenvalues has this sort of funny shape. We'll come back to this in a second. Okay, So some people ask me, first of all, what does it mean to scale? Like, what do you mean here? So when we say scaling in these neural networks, we say, okay, we really are talking about increasing the model size. So that means the space that we're actually minimizing over. All right. And how do you do that typically? Typically, it means increasing both width and depth. Okay, so there's some sort of optimization or sort of proportional regime where they increase both the width and depth. So here's just an example of this. So here's an example of how they do scaling on transformers, or one example. You have your model sizes, which are going up. Okay, you have your transformer layers. You can see that they're increasing in some way. Your attention heads are also increasing as you're going up. So that means you're increasing both width and depth proportionally to each other. Okay. So we say something like model size, but we're actually, and then that corresponds, of course, to the model size increasing, but we really mean sort of increasing width and depth. Okay, so now once you have figured out that you're going to fix that sort of architectural or scaling, now you go and you solve it with a stochastic algorithm. Now you have to choose things. So what people do in practice is they need to answer this question: how do you actually scale batch size, learning rate, momentum, weight decay, all of this as a function of your model size? So you do things like this, right? So you run your atom learning rate, say whatever, many times. You test it on some small model, then you increase, you see, and then you try to predict what happens in the larger models. You say, okay, well, the trend says that if I use some big model out here, I should predict that it goes like this because this is what the trend is saying it should do. Okay. So we have to know how to do this. So this all leads to sort of a theoretical question. Okay, and this is what people call scaling laws. So scaling laws are, you have precise upper and lower bounds on your loss function as a function of the number of iterations, samples, parameters, or number of neurons. And this sort of really differs from the way we do traditional optimization analysis in that we can't really do worst case. So worst case here would sort of say you have to work for all D. It has to be true for every D. But here we actually need to be able to optimize in D. We need to understand how the sort of landscape changes as a function of the model size itself. So another way of doing this is you need to think of your optimization problems now as optimization problems that are growing in size. And you want to understand how it changes, how the loss changes as your space changes. Okay, so that's what we need to be able to do. Okay, so I'm going to talk to you about something that came out, which is really, I think, was like the one that made ChatGPT actually sort of work and things. So we're going to talk about compute optimal scaling laws. So in sort of, I would say, recent years, we can use these scaling laws to answer sort of downstream tasks. And one of them is this compute problem. And so this is this idea that the limitation that we're seeing now in our models isn't necessarily data. We sort of have a lot of data. Okay, they scoured the internet at this point for LLM, so they have the data. The thing which makes it so difficult to do anything with it is that we don't have compute. And I'm sure all of you have had this problem, maybe. You only have, you can't get a GPU, or it costs too much to use your GPUs, right? So our limitation now is a compute. So this brings this interesting question, which is that for a given compute budget, and you have infinite amount of data, how do you best allocate your resources? How should you choose your architecture? How should you choose your number of parameters so that you're not wasteful in compute? Okay. So let me just formalize this as an actual math problem, okay? So you can write this down. So here you go, I'm minimizing some loss function. I'm gonna let D be the space for which I'm minimizing over, number of parameters. So a really simple, compute computation is just compute, which I'll measure in flops. Okay, let me be abusive here because flops is actually per second, so okay. But flops is compute, and it's equal to iterations of my algorithm times my number of parameters. Okay, that's just like a simple thing. Yeah.
So previously, one of the parameters I've seen people optimize over is, how much, like you can trade off compute between, say, making the architecture bigger and using more data.
Yeah.
So is here the amount of data we train on in, like implicitly a parameter?
Yeah, so it's here, the reason is that you have infinite data, so you usually don't, you reuse your data. It's always sort of beneficial not to. So by iterations, in stochastic, it's sort of a measurement of number of data points. Yeah, you're using, yeah, great question. So it's just a, yeah. Yeah.
I guess the question is the size of the batch size, right?
Yeah, so you can incorporate batch into here. You would just do batch times iterations times that. Yeah, yeah, and do the same thing. Yeah, I'm just letting batch be one for simplicity here. But yeah, you can incorporate that as well. So let me just show you what the picture of this looks like to give you a formal definition of this problem. So the idea is you would run SGD for t iterations on different d values, and then you would plot them. So here I'm plotting them here. And then because of this relationship between compute, iterations, and parameters, you can rewrite your loss function as a function of flops. So you would rewrite it as a function of flops, and so you can plot your loss as a function of flops. Okay, and so when you do that, you get these curves like this. And so then the fixed compute question is the following. If you fix the number of flops, you have infinite data. How should you choose D so that you get the best loss? Because the number of parameters is something you can pick, right? So another way of writing that is that it should be D star, the function of your flops, is the argmin of your loss of flops in D. Okay. Another way of stating this question is, when is it more compute efficient to continue training, or when is it better to actually increase your model? This is the same question. Okay, so let's get an understanding of what's happening here. So from this picture, so here I'm plotting different Ds. Okay, I'm fixing my flops to be 10 to the 7th. Okay, that's a gray line. So what do we expect to happen? We expect some sort of trade-off, as someone was pointing out. Why do we have that? So like, let's say D is equal to 1600. Well, 1600 parameters is pretty small, which means that you don't have a lot of expressivity in your model itself, right? So what happens is that you can solve it, it's easy, it's cheap, but eventually you stabilize at some value just because you can't minimize any further because of the expressivity, okay? So you say, okay, well, I can increase the number, the D. Let's say I go all the way up to 51,000. Well, 51,000 is great. I have a lot of expressivity. I can get to really low loss values, but now every iteration costs me a lot more. So because I'm fixing my flops, I can't actually run the optimization algorithm for very long. I'm restricted in that regard. So I don't ever even make it down here. So you can see that the optimal D is somewhere around, I think, 1200 or 6400. Forget which one here. Okay. And you can think about what's going on here. This is really constrained in some sense by expressivity of the model capacity. That is, what should you have done? What you should have done is you should run your algorithm up until you reach the stationarity, this limiting value, and then once you reach that, if you had continued training, you're just wasteful because you're not improving the loss at all. You should be better by increasing D. Okay? So we call this line here, when we do this for every flop, we call this line the compute curve, okay? But that's not the old, yeah.
I think that for the iteration here, you think that the iteration is linear in D?
Great question. Not always, not always. So that's chinchilla, that's the chinchilla scaling. So our goal is to try to understand where does the chinchilla scaling come from, or if it's not optimal in some sense. But also just to understand what potential like the curves look like. So this is one potential sort of shape of the compute curve, which is that you go down, you reach stationarity, and you should stop. You should increase D. But you can get other curves. So this maybe is more surprising. What you can get here is you can get something like early stopping. It might be actually more compute efficient to actually stop running your algorithm much earlier before you reach stationarity. So you can see here, I'm reaching stationarity down here, but my compute curve is way stopped up here. Why do you get things like this? This is because you can have signals that get mixed up in some noise. And you can potentially solve through them in the optimization. Like you can actually go and decrease your loss further and work really hard, but it's not compute efficient to do that. It's actually more compute efficient to increase the size of your model. Okay? So this is an example of some sort of noise signal problem. So I want to show you where this question came from. It really came from empirical work and industry work because they really do have to do this. They really do have compute budget. They cannot run their giant models for years and years and years. They only have 6 months or something, or a year to run their thing. So they really need to know, how do I choose D correctly? How should I scale D? And then choose all the other hyperparameters as a result of that. So what they showed is the following thing. So what they ran is LLMs. This would be called chinchilla. They ran their stochastic algorithms repeatedly. They plotted their loss as a function of flops. And then what they did is they assumed a functional form for their loss. And they just fit that curve to this functional form. Okay? And then what they empirically observed is something which Misha was just commenting on, which is called chinchilla scaling, which is that they've observed that using real LLMs, okay, doing this sort of fit, that the best choice of way to choose the number of parameters is exactly to choose it as D. T, number of iterations is on the order of D, linear. Okay? So our goal is to try to understand that. If you want, this is the number of samples is on the order of D too. Okay? And what? So my compute is measured by this, is just saying that the best D, I should basically stop running my optimization algorithm after D steps. It's not worth it in compute. That's what it's saying. You should stop at D. It would be better to increase your model size than to continue training it. That's what they observed empirically, okay? And one of the questions is just, where does this come from? I mean, this is all empirical, all empirical, okay? So the goal with this work was really to do this sort of theoretically, at least trying to understand some very, very simple model where we could analyze everything, which mimic the same behavior as the real LLM. So you saw the scaling, you saw this sort of power law, these curves appearing, and but you could analyze it completely. So you could understand why and what was affecting all of these compute curves. So the idea here is we're going to use what are 3-parameter neural scaling model, which we can derive everything explicitly. And we're going to have 3 parameters, which one is going to be the data complexity, one is the target complexity, and then one is going to be our model size. And what we're going to show is that on this very, very simple model, there's going to be 4 qualitatively distinct compute curve shapes that you can get. And it's all going to depend on how the data complexity compares to the target complexity. You saw 2 of them. One was the capacity of the model. That was the one where you just go straight down and you stop. I explained this poor features embedding. This is this idea that you have to embed your data in some other way. Okay? When you do that embedding, it can cause noise. You can lose signal from your data, and as a result, it can slow you down in training. So you can go down really fast first and then slow down in training. So you get sort of a stop early thing in terms of compute before you get to capacity. But you can also be constrained by the actual algorithm itself. These are stochastic algorithms. They have noise from the stochasticity that can also affect the training dynamics. So the question is effects of the sort of algorithm itself. And what we'll show is actually something really cool, which is that for a really, really large portion of your alpha beta plane, that you recover chinchilla scaling. So even on this simple model, you can actually see under what sort of data complexity and target complexities where you actually get, so it flops to the 1/2, but flops to 1/2 if you translate everything over, is the same thing as chinchilla scaling. So what is the model? The model is really simple. We just wanted, again, to mimic LLMs. I'm not going to be able to actually do this on an LLM because that would require too much, it's more complicated. So the idea is that I'm going to take my data, lives in RV and embedded in RD by a random matrix W. And I'm just going to run streaming SGD off of it. Okay? So what am I going to assume? So I'm going to assume that my W has entries, which are 1 over D. I'm not going to train them. Okay? And the main assumption, in order to get the scaling part, is that I need my data to have what is called a power law distribution. So you need that your entries of your data to be normally distributed, and the key thing is they have this j to the minus 2 alpha covariance. So this alpha is going to play a role. My targets, I'm also going to have a power law distribution on them. Okay. And the main thing which is going to matter here is this matrix DWW transpose D, where D is a diagonal matrix. Okay? And so the goal of compute optimal, yeah. Oh yeah, my target is X transpose B. B, I'm going to be a vector, which has as entries J to the minus beta. You can make this normal too. You can make it random. It doesn't matter. This is not predetermined because there's not a W on this one. Yeah. Yeah, exactly.
What's going on in the right column here?
Oh, this is because, so the assumption here is usually vocabulary size. So the size that your X lives in, your data, is usually the vocabulary. You don't have a choice over that because it's data. It just can be anything large enough so that when 2 alpha is bigger than 1, it just needs to be, it can be anything. And when 2 alpha is less than 1, you need it to be proportional. And this has to do with summability of your covariance here. Yeah.
So generally speaking, you want the true X, the true function to be kind of a large dimensional, but you are restricted to some observed features.
Exactly. Exactly. And you get to pick the D. Whereas you don't have a choice over the V, right? Like the V is just the it's vocabulary and language modeling sort of size. That's exactly right. Yeah. Yeah. We'll see it. It'll clear in a second. It'll appear. I'll show it to you. Just, it's there. So then the idea was the goal of this, right, is compute optimality. So you're trying to minimize in D. And the big question that you're really interested in is that you know your optimum is going to look like flops to some power, and your D star is also going to look to flops to some power. You're interested in those powers because that's like the big money gain out there in the world, right? If you can figure out the exponent, you can predict ahead of time what size D you should use, and you can really, really improve the performance in the long run. So it's all about the exponent there. There's a lot of work on this. People have studied this model. This model is actually what I created to do these pictures. They're so clean scaling, that's why. So I was using that here. I just want to point out that this is really, really different than what people do for mini-max optimal. Again, they usually don't optimize in the number of parameters. So the number of parameters here is the essential thing that we're trying to deal with. Okay, we usually don't take it. So I wanted to return to where this power law comes from. So power law covariance structures actually appears a lot of places. So in one of these places you'll see is that they appear in real data. So I showed you that CFAR5M picture. Indeed, if you looked at its covariance, it would have a power law distribution. So this is a power law distribution of CFAR-M. If you take activation functions of it, entry-wise activation, it becomes even more power law. So that's what these green curves are. These are simulated power laws with different exponents. Okay, language has this. Where does language get this from? If you look at word frequencies follow something called Zipf's law. Zipf's law has like power law distribution, and then you stick it and embed it into language models, and you start to maybe see that appear. Okay, so power law distribution is around. It seems to be in real data. Okay? So what can we do? How do we actually predict all of this? This comes where this K hat is that you can show that the expected loss under SGD, under that model, follows the Volterra equation, okay? Provided that you condition on W, and the Volterra equation is just a function of your forcing, which is your gradient descent, and your kernel. which is the effect of SGD noise on the loss itself. And if you look really carefully, it all involves this k hat, which means that it always just involves the eigenvalues of k hat. I'll skip this thing here about that. And so what you can do is, this is still a random matrix because k hat has this w, which is random, but you can replace this k randomizing with a deterministic equivalent for it. So you can replace them with a deterministic equivalent and end up with getting just, oh, sorry, these should be t's. I was changing between k and t last night. Apparently I missed a few. This is a deterministic equivalent, and so you can actually have a deterministic formula for the behavior of the algorithm without actually running it, by just knowing the eigenvalue spectrum of this k hat in this deterministic equivalent version. Okay? Yeah.
Is the doubling like a random feature model, the power law, like if we have an amplitude, if you can propose an original data?
That's a great question. So that comes from, so it doesn't appear automatically. So you have to impose it. Where you could get it from, the activation function. So your activation function could force it to have a power law distribution that outputs. Yeah, you would have to, it wouldn't be Rayleigh, you'd have to do some sort of funny thing that creates the power law there. Yeah, but yeah. And the other thing is, with what seems to be very clear with power law is that it's, once you're power law, you're always power law. So like, it's really hard to do transformations. You can create them, but the standard ones aren't going to remove the power law distribution. So if your data starts with power law, you're probably going to end up with something power law. Maybe not the same exponent, but definitely has some power law distribution. Are there other questions? Yeah.
About the intuition of K, I couldn't figure out the physical meaning. What is representing that loss?
Yeah. So in this model, this is a great question. In this model, if you took the Hessian, that's K. Or actually, the reverse of the K would be, the Hessian would be W transpose D W. If you did the reverse of that, so you put the D on the other side, that's what this K hat is. So it has the same eigenvalues as the Hessian. Cool, so you have this deterministic equivalent, it actually works across all D, and you can predict, and it just works. You can solve it, everything is beautiful about it. It's really nice. What makes this nice is that it's actually relatively easy to get these curves. If you've ever tried to get a compute curve, it's really annoying. Yeah.
That iteration, like a couple of slides that.
Yeah. This one?
So was one, one before.
This one?
Yes, yes. So that's your STD iteration, right?
Yeah.
And
Yeah.
you be this matrix vector multiplication W times theta T. So that will cost you D times D blocks.
Yeah.
Right?
Yeah.
And then you are taking your regime of D is actually D over D going to R, and it's going to infinity. So how? So which makes me believe that for iteration you're taking more than D square logs. So
Yeah.
in effect, D square 10T,
Yeah.
it should be cube root.
So I'm abusing this idea of flops. You're right. The argument here is that you don't have a choice over V, you have a choice over D. So flops is maybe the bad term, but they measure compute as sort of iterations times number of parameters. It's like you said, there's more compute involved in it, but it's something that is fixed, like you don't have control over. Right, like it's like it's part of the data or something. It's there, so you can't optimize it. Yeah, it's a good question. Yeah, I was abusing it because that's how they use it. Okay, so what can you show with this deterministic equivalent? Well, the first thing you show is that the loss is actually, even though it's some sort of implicit equation that you can completely solve numerically, it's really just F plus K, and this happens to just be the effect of power law distribution. So you can actually express this, you just need to understand your forcing in your kernel function. So this F and K, wow, I really missed a bunch of T's. I'm really sorry, you guys. And so each of these components is just a function of T to some power, D to some power that you can write down. Where do these powers come from? They come from the eigenvalues of the Hessian, or this K hat matrix that I was showing you. So the idea is that you have these power laws, which look like J to the minus alpha. So you have these sort of spikes in here. But the problem is that you hit it with a random matrix, W, which distorts the spikes a little bit. So it adds a little bit of a Marchenko-Pasteur around each of these good signals. And that because they're going J to, it's getting bigger and bigger and bigger, that Marchenko-Pasteur is eventually getting closer together, and it's creating an absolutely continuous part of the spectrum. So you're getting sort of different components, and that's what is represented by these different F values. So FPP is just the pure spikes. FAC will represent this absolutely continuous part, and F0 will represent what happens. There's a spike at 0. So there's a stationarity value, okay? There's also the effect of SGD, which I'm going to call KPP here. And again, it just comes from the eigenvalues of this thing. So what you show, which I think is really cool, is that you get different, a phase diagram for each of for different alphas and betas. So if you're all in alpha and betas and this region 1, your loss curve is just the pure spikes plus the point mass at 0. So these are compute curves that just go down and they stop. Okay? If you're in phase 2, then you have 3 components. You go down, then you go down again at a different slope, and then you reach stationarity. This is because you hit with some of that absolutely continuous part, which is that noise from that Marchenko-Pasteur is actually obscuring some of the signal. Okay, so these 2 phases here are all stuff about gradient descent in some sense. In phase 3, you see the effect of SGD. So phase 3 here, this means that your alphas and betas are in that regime. Then you actually see SGD taking hold. And then similarly in phase 4. So just to give you a picture, again, what does this mean? It means that, so if I have any alpha and beta in this regime too, my loss looks like this. So I see a component which goes down, and then it kinks down again, and then it stops. Okay? So this is the pure signal noise, pure signal. This is the effect of the fact that your noise gets hit with a random matrix. It slows you down a little bit. It makes the signals hard to find, and then you reach your capacity. And then you can find compute optimal just by knowing that it has to occur at one of these points here. Okay? So you can do that. You have explicit formulas for all of this. You have everything is deterministic. You removed all the randomness. So you can solve for what should be the compute optimal and understand how all these compute curves. And one of the things you see, which is super cool, which is completely amazing in some sense, is that there's a huge region. So if you look at this region here, this region here, for which your optimal D is just flops to the 1/2, and that agrees with the chinchilla scaling. So this really simple model produced a big swath of things which have different shapes of their loss curve, but they all give the same chinchilla scaling regime. Don't seem impressed, but I thought that was cool. There's a lot of math that goes on here, and then all of a sudden you end up with flops to the 1/2 of the answer. Is like everything cancels. There's no alpha and beta dependence, nothing there. It's pretty amazing. So why is this super useful for practitioners? This is essentially says that like if you were to guess like which curve, which regime you should guess, you should probably guess this D is flops to the 1/2. You should probably use chinchilla scaling. There's no alphas and betas you have to compute, and there's a huge portion of the phase plane which actually has the exact same one. So maybe the empirical people got it right. Okay. That's a great question. I do not know the answer, and I would love to talk to you about it. I would love to do that. It's a little bit complicated, but yeah, it'd be super cool to do it. Cool. Any other questions? I'm gonna move on. Yeah.
We cannot tell anything to empirical people, right? People got it wrong.
They already figured it out? Okay, so maybe I can convince you otherwise. Okay, so yeah, it feels like this. Okay, yeah.
So, okay. In your picture, half the plane is good, so it agrees with empirical people, but half the plane is.
It's not good, right?
Don't worry,
Yeah. Yeah, so let's just say that the empirical work is a little bit fishy because it depends on how you, like, they have to fit various power laws and they have to make an assumption about how their loss curve. So there's all sorts of weird fishy things going on about it. There is ways you can make it, and that people have shown that the chinchilla scaling law doesn't work for everything.
because it's extreme extent, like in this case, so the F to the 1/2, like that, we're gonna interpolate between two extreme,
So it's here, you can see it extrapolates. So these are continuous across these phases. So as you go across phase 3 into phase 2, you'll see this is how it changes. It's amazing that that becomes 1/2 in that region. Yeah,
So in your model, kind of the label is noise free.
Yeah.
In some of these others, scaling law research, the one that you cited at the end, right?
Yeah.
They started off saying that there's a label noise.
Yeah.
They recover, different behavior.
So most of the previous stuff which does this, they don't do the random matrix W because they can't do it. You can add label noise into what I'm doing, and I didn't do that. And actually, it's a great question because it doesn't really change anything. Like it decomposes a little bit of things that I'm hiding under the rug, especially in it changes the regime underneath here. So below 2 alpha being less than 0.5, it'll change some stuff.
I mean, the random noise assumptions, even at even as your D gets bigger, like the device will go 0, right?
Yeah.
The random noise will say that you just always get a bit of
Yeah.
randomness if you cannot compress, right?
Yeah.
Does that change things on the scaling law?
It's an interesting question. You have to be a little bit careful. You can't use order 1 noise because then you won't get this nice scaling law. You still have to get this to appear. So it's a little bit hard in the linear model to do that because of that. So that you have to have sort of a noise, which is also sort of going to 0 as a function of D in order to,
But instead you can calculate the loss.
Yeah.
By comparing to the true function rather than.
Yeah,
noisy
but you
base.
won't get a scale, you won't be able to reproduce a scaling law.
Okay.
Because it compresses it so much that all of the curves in least squares type problems end up all going to the same value.
Then your hypothesis that the practice of fitting the real data to the neural network are not noisy.
No, I think they are noisy. It's just that this model can't handle that to reproduce the scaling. Yeah. Yeah. Does that make sense? Like it can't reproduce that effect. It's a good question. Okay, if I have some time, I'll get to, sorry. Okay, so maybe going into Misha's question. So here's what I wanted to do. So there's this belief out there, and we now have these scaling laws, and it was like, okay, the empirical people are correct. But this was always SGD. So now you can say, well, can you actually do something better? Like, can you actually, use this style of analysis, create an algorithm, which actually can beat SGD in some sense, do better than that in the compute curve, okay? And empirically, the answer has always been no. But this is really flimsy, okay? The empirical answer is that all algorithms don't matter. They give the exact same compute exponent, okay? And that all we're really doing when we're saying atom is better than SGD with momentum, they're constant. That's it. Okay. So this led to this question, well, can you actually devise an algorithm that provably outscales SGD? Okay. That is, can you actually have an algorithm which gives you a better compute optimal exponent than SGD? So this D star. So how do you do about it? Okay, so we started with SGD. We never use SGD in practice. Even if you use something like it, you probably use momentum added to it. Okay, So the idea here is let's look at momentum, but now we need to be very careful with momentum. With momentum, we're talking about is we need to allow our learning rates to all be time and dimension dependent, because we need to know how they scale. Okay. So this is this question of, okay, can I choose these learning rates as a function of T and D so that I actually can create a newer algorithm that outscales SGD? Yeah.
Why couldn't we just fix some of them?
I will show you why. It doesn't work in the scaling. Yeah, it doesn't outscale. That's the problem, which might be why it looks exactly the same as SGD. So that's a great question. Okay, so why do we actually use momentum? I'll go through this quickly since I think most people here know. In deterministic optimization, we basically know it works better. If we choose good learning rates, we choose good momentum parameters, everything works better, right? We get acceleration. So just for notation purposes, I'm going to call classic momentum where I have learning rates which are just constants or D-dependent, so they have no time. And if you think about Nesterov's acceleration, you can rewrite it. Sorry, I rewrote all momentum in this form because you can rewrite it in this way, and it's a time-dependent sort of momentum thing. But if you ever have tried to do momentum stochastic, you immediately run into certain problems with stability. I don't know how many people have tried, but it's actually really hard to make this algorithm stable. And in class, in what we have been told is, just as Misha said, we should just choose it constant. That's what they said. They just said pick a 0.1 or beta 1 and beta 2 should be 0.9 and 0.999. Like why those numbers? Where do they come from? And are they actually supposed to be constant? Okay. So what I'm going to do here is I'm going to work with a general momentum form. So I have my momentum and I have my update rule. And again, the idea is that I'm going to allow my hyperparameters to both be T dependent and D dependent. Okay. So this covers basically everything, a lot of momentum style stuff. Doesn't do atom, but you can kind of imagine some things about atom. This is a hope that we could eventually do atom and understand what's going on. Okay. And so our goal here is, can we choose these hyperparameters? So I'm just going to look again at this model, same model as before. Okay, nothing changed. All right. So what's the first thing you do? And this is really fun. First thing you do is you should choose it constant. So you should choose your momentum to just be a fixed number, 0.1. Okay. And I'm going to allow my learning rates to be D-dependent. Okay, so I'm going to choose these guys to be D-dependent. And what you first see is that this has the exact same learning dynamics as SGD with just a different learning rate. Okay, so you could have run SGD with gamma 2 plus gamma 3 over delta, and you would have gotten the exact same learning rate. Why is this? So this is super important to try to understand. So the idea here is that delta is fixed. So when you go and you can look at the first equation, you can just solve it. It's just a recursive thing. It's an exponential. Okay, it's exponential, and which means that the really fast ones decay really fast. So you're really looking only at current iterates. Okay, but you're in small batch. You're in stochastic small batch thing. When you're only looking at maybe the last 10 iterations, your gradient hasn't changed enough to make any difference. So it's basically exactly the same thing as what you currently are at. And so if you think of it that way, you can plug this back in. It's exactly the same thing as you currently are at. That just means you're doing SGD with a different learning rate. And you can actually see this. You can actually run this on real data with LSTMs, and you can actually see that they match. They basically are exactly the same with different learning rate. And it's just intuitive, right? It's small batch effect here with the fact that you have an exponential here. So that immediately says you should use longer momentum, long time momentum. So you say, okay, I'm going to use Nesterov. So this is where I was going to do. Here is Nesterov. Okay, so why does Nesterov have a problem? Okay, so the problem is, let's look at, you can always, sorry everyone, this is my makeshift thing here. Okay, you can always choose gamma 1 to be 1 by doing a little trick here, okay? By just sort of pulling things out asymptotically. So asymptotically, I can make it 1. If I make it 1, then I'm going to choose gamma 3 times gamma 1 to be the new gamma 3. So my new gamma 3 is equal to gamma 1. My old gamma 1 times gamma 3. But if you do that, if you pull that out, you can see asymptotically that gamma 3 times gamma 1 just becomes this gamma tilde, this constant. So what you're really doing here is you're really putting a constant here, which is gamma tilde, and a constant here, which is gamma tilde. Okay, so why is this a problem? This is a problem because you're in stochastic. You're in stochastic, and so this has a noise, but it's a very different noise than what the YT is accumulating here. And you only get one parameter, gamma tilde, to fix both of them. This is building up noise from the stochastic gradients over time, and this has just one stochastic gradient, has a fixed noise, and you only get one parameter to choose. So this, if you guys see this, this is this gamma tilde, Nestra. And so there's no way to choose this gamma tilde so that in this model, you actually end up stable. Because you have to balance these two noise terms, which are building, one is building up over time, one is a very distinct, and you need to make sure that this thing is actually a stable algorithm, and you can't do it. So this immediately sort of tells you that you need to have two different time-dependent, you need to have two different learning rates. One to control the size of the stochastic gradient, and one to control one which is building up stochastic gradients over time. So you have to have, and they should be on different orders of magnitude. Make sense? Okay. So now you try the first thing. The first thing you should try is, okay, can I make it stable by choosing two different things? I'll just choose this term to be constant, something different but constant than this one. If you choose it to be constant, what you immediately see is that you have to choose it to be 1 over d. Okay? Has to be 1 over d. So this needs to be 1 over d. So why is now this a weird problem? Well, this learning rate is way, way smaller than this learning rate. So the problem is that for the first d steps, this thing is not doing anything. It's not helping you at all. Because this is like 1 over d, and this is like order 1, let's say. So you're just not doing anything, and you can see that. So what happens here is that you start, this is this green thing, you'll see it looks like SGD for the first d steps, and then all of a sudden it splits off and you get better improvement. The problem is that compute optimal could occur right here, in which case you're just SGD again. So you do get acceleration, but only after d steps. Okay, so now you guys should tell, how do you fix that? Okay. Well, how would you fix it? You would fix it by saying, okay, I shouldn't have used a constant here. Let me use a time-dependent thing. So you can use a time-dependent thing, and the thing you should try to use is something like 1 plus t to the negative 1 over 2 alpha. And if you do that, then you actually get acceleration for all time. And how does it come about? It's actually really cool to see this. So where does this thing come about? It's like the largest sort of learning rate in some sense as a time parameter, so that you're on the edge of like stability here. So if you had chosen gamma 3 to be d to some power, and you chose a power which is bigger or smaller than 1, it will go for a little while and then it will diverge. So those are those divergence things. And the orange curve is exactly if you had used this learning rate. The same thing here is if you had used 1 plus t to a power and you had chosen a different power than 1 over 2 alpha, you would go for a little while and then it would diverge. And then what you want to do is you want to track along the edge, and exactly this thing does it. Okay, but notice it uses this exponent. Okay. And so you end up sort of fixing this problem where you get sort of the orange curve, which you get sort of the acceleration throughout. Okay. So I'm just going to say how you actually can do this, how you analyze it. You can use the exact same theory as before. Everything works with this momentum. You can analyze what is the effect of these different learning rates and their powers on D. and end up with compute curves and everything. All they end up with is that your functions are time changes, and your time change can be represented more broadly as just gamma 2t, which is like an SGD, plus the learning rate of this integral squared, which has to do with the second term. And then you're just sort of maximizing these. You want this term to dominate the loss curve while still remaining stable, and that's where you get the t to the minus 1 over 2 alpha. So if you can use dimension, it doesn't help. You would use a 1 over d, essentially. Because if the exponential doesn't work, you use something like a d-dependent time, it just doesn't help. It doesn't add anything. You need some sort of time dependency. Cool. This is what you get, the same sort of curves, but now you just get different slopes happening. So, and it's really fun to do this. I'll go through this fast. You can run these deterministic equations, and you can really see that you really do see speed up as compute optimal curves over when you use these sort of algorithms. Okay, I'm gonna skip some. I can write down everything. So maybe I'll just say a few things about this. How does it actually affect on the rate? So normally in deterministic optimization, you get like a square better than as like gradient descent. You don't quite get a square better, you get 2 times minus kappa 3. Okay, and kappa 3 has to be bigger than 1 over 2 alpha. So this would be true of like alpha over infinity. You get the square improvement, but you don't quite get it. Yeah. So then you improve chinchilla scaling. Yeah, exactly. Sort of. It's more complicated, but yeah, it improves chinchilla scaling. So they said that there's actually a way to improve chinchilla scaling. That the TD was just like by potentially scaling your momentum parameters, which for some reason we don't actually do. Not sure why, but we don't do it. Okay. This is just to show you that this one that I was choosing, the thing I was calling Dana decay with the 1 over t, is actually optimal in some sense. You can do this for all d and t things here, and you can plot what happens, and you can see that this one's actually like the best one to use. I also just wanted to end because I did want to get to this. Of course, this is like super cool because you're like, can you actually do this on real data? Like, does this actually work? So we tried this on a 2-layer LSTM on some language data, and it sort of works. Like, so here we were just comparing with SGD. So here we're doing SGD in the black. Here's where you do like a momentum scaling, and you can see it does sort of improve, which is kind of fun. So it also mimics a lot of the behavior that you see in the power law of random features model. So the first thing you might say is you don't know the data exponent. So how do you find the data exponent? Well, you saw that, like, remember I said if I had chosen a data exponent which was like kappa 3 and I guessed it, it would eventually blow up. You see the exact, you can sweep over your kappa 3s and you can see the same sort of effect on real data. Eventually it will blow up, and you just want to find the one which doesn't blow up. So now you say, okay, can you transfer that information? So this kappa 3 seems to transfer well because it's like a data, it's just data exponent. It's not really model size. So it's something that's just really cool is that your model size is not really well defined. And these language model stuff, it's a little bit, but it's a little bit confusing with actually what they call D and those. But this is this idea that this kappa 3 can actually works across different model sizes. It's like transfer. So you just find it on a small model and it transfers over because it's somehow related to the data exponents. It's not a model size exponent thing. You're sort of removing that. Okay. And then what we saw is that you actually really do get improvement over SGD, which was kind of fun. So, and this was on real data. So I'll just end there, and these are the 2 papers, and say thank you.